Hi there, folks. Today we're looking at solving logarithmic equations. And if you look at this, the first thing we're going to look at is the properties, the inverse properties for logarithms. And we've seen these previously in a different lesson, but here they are again. And last time we focused on one of these, now we're going to focus on the other one. They both kind of say the same thing. They're showing that a logarithm and a exponential function of the same base will cancel each other out. And here, this is the one that we've used previously as this first one. But basically it says, hey, if I have log base b and b raised to a power, a logarithm with base b and an exponential function with base b, log base b and b to a power cancel each other out. I'm just left with the exponent, okay? Likewise, if I do the same thing but in reverse, here I had log base b and b cancel each other out. Now I have b raised to a power and log base b. Well, it's still the same result. B raised to a power and log base b cancel each other out, and I'm just left with the r. Okay? And really, it's the same property, but in reverse. And when you think about it, one of these is used to cancel out an exponential function and get the exponent. The other one is used to cancel out the logarithm and get what's left inside the logarithm. And so this is the one we're going to kind of focus on today. All right? This is how we get rid of logarithms. We undo them by using an exponential function of the same base. All right? And this looks a little wonky compared to what we're used to in terms of solving equations, all right? So solving logarithmic equations, we're going to rewrite each side of the equation as one logarithm. So we have to condense things into one logarithm using our properties of logarithms. And then we're going to undo the logarithms using the inverse properties, or specifically using that second inverse property. And then we just solve what's left. After everything is canceled, after the logarithms are gone, we solve whatever I have left using previous solving methods, okay? For example, if I look at something like this guy, once again, I want to condense each side, and I can just do each side individually. So I want to condense this into single logarithms. So over here, I have log base 2 of 7 plus log base 2 of x. Remember, addition becomes multiplication in logarithms. So I can change this to log base 2 of 7x. The addition of two logarithms, well, that becomes multiplication inside the logarithm. That's my properties, okay? And now from here, I want to use that special property that I had written up there that says this: b raised to the log base b of r equals r. And so this is where things get a little bit weird. We kind of have to think back, and one of the things that I think helps make this make a little bit more sense is when you think back to solving exponential functions, but solving them by getting common bases. We had a really special step, like if I gave you something like this, like 2 to the 5th equals 2 to the 2x, when the bases are the same, you know that you can set the exponents equally to each other. Okay? But what's to stop us from doing that step in reverse? In other words, if I have 5 equals 2x, what's to stop me from saying, hey, I can rewrite that as 2 to the 5th equals 2 to the x? Or better yet, I want to write that as, if 5 equals 2x, I'm going to write it as, 6 to the 5th equals 6 to the 2x. Okay? In other words, taking two things that are equal and saying, hey, these are now going to be the exponents of two things that have the same base. All right. And that's kind of what we do here. We kind of look at this and say, you know what? I'm going to rewrite each side of the equation. I'm going to rewrite this side as 2 to the log base 2 of 7x. And I'm going to write this side as 2 raised to the log base 2 of 35. All right. And that seems crazy to kind of approach it that way and to look at it that way. But, if two bases the same, means I can set the exponents equal to each other. Well, that means if I have two things that are equal to each other, I can certainly write them as exponents and with the same base. All right. And so that's what I've done here. I've basically said, hey, these two things are the same. So I'm just going to write them as the exponents and have the same base. And really, that's an okay move because I've done this in reverse. Well, of course I can go backwards. But the reason I choose 2 as the base here is because essentially the 2 raised to a power and log base 2 cancel each other out. And I could have chosen any base in terms of rewriting these each side as an exponent. I could have done 3 raised to the log base 2 of 7x equals 3 raised to the log base 2 of 35. But 3 doesn't help me in this situation. The only one that helps me is the 2 because the 2 cancels out with the logarithm. Okay? And so as I cancel all this stuff, what I'm left with is 7x equals 35. And this is an equation that I can easily solve. I divide each side by the 7, and I get a 5. Okay? And the last thing I should do is I should plug this back in and check it. Really, for logarithms, remember, I can't plug negatives into a logarithm. That goes back to the nature of logarithms themselves when we looked at the graphs and those kind of things. Negatives didn't work when we think about the asymptotes on the graph. Okay? Negatives don't work when I plug them into a logarithm. 0 doesn't work when I plug it into the logarithm. So just make sure I have an x value that doesn't give me negatives or 0 inside the logarithm. Okay? If I look at this one, same kind of thing. I'm going to rewrite this as one log first. This is log base 3 of addition becomes multiplication in the logarithm. So that's 5x squared equals log base 3 of 15. And so now here's this kind of strange step. I need that log base 3 to cancel out, so I need 3 raised to a power. I just rewrite each side of this equation as an exponent. It's 3 raised to the log base 3 of 5x squared. And again, I've chosen 3 because I know that's the thing that's going to cancel with a log base 3 equals 3 raised to the log base 3 of 15. And so I just take each side of the equation, I rewrite it as the exponent, and now things cancel because I chose the correct base. Log base 3 and 3 to a power cancel. Over here, same kind of thing. Okay? And so what I'm left with is 5x squared equals 15. And now I can continue to solve this thing. I divide each side. I take the square root of each side. And so I end up with x equals plus or minus the square root of 3. But as I think about plugging each of those values in, if I plug the negative value in, right here, it's going to give me a negative inside the logarithm. That's no good. So really, that's an extraneous solution. My only answer is x equals the square root of 3. Okay? Only the positive version this time. If I look at this one, once again, I'm going to rewrite it as one logarithm first. Sorry, that's a 7. And again, its addition becomes multiplication. So when I multiply this, that's an x squared minus 2x minus 3. I'm doing some quick multiplication there. And one of the things that I do is I take a little bit of a shortcut here. Instead of literally rewriting the entire equation as 7 raised to this power equals 7 raised to this power, yeah, each of these is going to be the exponent. I just put a big 7 down here and say, okay, 7 raised to this power equals 7 raised to this power, instead of rewriting it, okay? And maybe it helps if I erase this and I put the equal sign down here. Oh, there we go, all right? So just to save myself a little bit of a time, a little bit of space, a little bit of effort here, I rewrite it like this, and now I say, okay, these cancel. Over here, these guys also cancel. And now I can finish solving what's left, okay? This is a quadratic. I'm going to subtract that 5 from each side. And now I build a bridge. This factors into an x minus 4 and an x plus 2. I set each factor equal to 0. And now I solve each, and I get x equals a 4 and x equals a negative 2. However, think about plugging those back in. If I plug the 4 back in, I get positive values in the logarithms. But if I plug the negative 2 in, I'm going to get negative values in the logarithms. It's not about the x being negative. It's about what I get when I plug it back in. Negative values are okay for x as long as it doesn't result in a negative inside the logarithm. So this is the only answer. This one ends up being extraneous. Okay? If I look at this guy, once again, we're going to condense this thing into one logarithm. So right here, I've got some multiplication. Here I have some more multiplication. Remember, multiplication becomes exponents in the logarithm. So this is going to become log base 2 of x squared minus, this is going to become log base 2 of 3 to the second power, which is 9. Equals the 4. And now I keep combining these. I say, okay, subtraction, that becomes division inside the logarithm. And now I can undo this thing. And students get really tripped up here because there's no logarithm on the one side. Let me rewrite this as the exponents. Here, I'm going to use a base of 2, so 2 raised to the log base 2, x squared minus 9. I'm not going to use my little shortcut thing just yet. Over here, I use 2 as the base. This side of the equation becomes the exponent, so that's a 4. And here's the thing. There's nothing to get tripped up about. Right here, log base 2 and the 2 cancel. Great. On the other side, it literally says 2 to the 4th power. So I've got x squared over 9 equals 2 to the 4th power. Well, that's 16. All right, I know how to handle that. All right, and if you rewrite these, if you rewrite each side of the equation as, hey, base, and each side of this thing is the exponent, well, it should become obvious that that's, hey, 2 to the 4th power. Okay, that's 16. Okay? And now I multiply each side by 9. Oh, I'm kind of running out of space here. Oh, no. That's x squared equals 144. I take the square root of each side, so I get x equals plus or minus 12. But you can probably guess where this is going. As I plug these things back in, I can't plug that negative 12 in because it gives me a negative inside the logarithm. So just the positive 12. The negative is extraneous. Okay? If I look at the next one, once again, I'm going to combine these. Addition becomes multiplication. This time I'll kind of show it from the perspective using my little shortcut thing. I'm going to say, hey, I'm going to use 3 as the base, so 3 raised to this power equals 3 raised to the power on the other side. Okay? So each side of the equation becomes the exponent. Over here, log base 3 and the 3 cancel. All right? But now, just being able to read this thing, and again, without using my little shortcut type thing here, it's easier to read when I actually rewrite the whole thing. Here, just be careful. That literally says 3 to the 3rd power, which is 27. And now I subtract the 27 from each side, and I continue to solve. Again, what I'm doing there, it's a little bit of a way to kind of cut out 1 or 2 steps that I have to write. Okay? And now I build a bridge, 2 numbers that multiply to a negative 27 but add to a positive 6, a plus 9 and a minus 3. I set each factor equal to 0, and I end up with a negative 9 and a positive 3. But once again, double check them, make sure that none of these give you a negative inside the logarithm. Now this one does. Okay, so that one's an extraneous solution. So the x equals 3 is my only answer. Okay? If I look at this guy, once again, I'm going to combine these into one logarithm. Don't be scared by the fact that this is a natural logarithm. Okay, those are still logarithms. They're just a special base. But it's the same thing. I still combine these the same way I would anything else. So right now I have subtraction. Subtraction becomes division in the logarithm. So this becomes the natural log of 24x divided by 6, which is just a 4x. Okay? So we'll do 24x divided by 6. There's my new logarithm. Equals the 8. And now from here, this is where students really have to reach back and think about, well, what in the world was the natural logarithm? Remember, the natural logarithm was log base e. And so the base of this logarithm is e, which means that's the base I need to use. E raised to this power equals e raised to this power. Okay? And so each side of the equation becomes the exponent, e raised to the natural log of 4x. E raised to the 8th power, all right? And now, once again, log base e and e cancel. That's what the natural logarithm is. So those cancel. I'm left to the 4x. Over here, e to the 8th power, I'm just going to leave it that way for now. That's going to be a job for my calculator. I divide each side. So I get x equals, well, now it's time to plug this into my calculator. Remember that little E button? We have to hit the second key, the shift key, and then the LN button is typically where it's located, okay? So I hit E to the 8th power on my calculator and divide it by 4, and I get 745.24. I'll just go 2 decimals here, okay? But again, remember, E is a number. The natural logarithm is log base e, so we have to use that e to a power thing that we did quite a while ago, all right? If we look at this one, there's no base written, which might concern you if you didn't know that when there's no base written, it's automatically log base 10. It's the common logarithm. And so once again, we combine these. Subtraction becomes division. And now from here to undo log base 10, I do 10 raised to the power of each side. Okay, so each side of the equation becomes the exponent, 10 raised to the power of each of these. Log base 10 and the 10 cancel. Over here, it literally says 10 to the 10th power, which is ridiculous. There we go. Nailed it. Okay, hopefully I counted the number of zeros correctly. Okay, and now from here, if I'm going to solve this thing, this is kind of a case where I might do something like cross multiply. Okay, so here I'm going to put this over 1. I'll cross multiply. Equals the 5, and now I divide each side. I sure am glad that I picked such a ridiculous value for this thing so that I get to write it 8 million times. I don't know what I was thinking, okay? Guess I thought it would be hilarious. Joke's on me. X equals, and then of course I can reduce this thing. Oh my goodness. Each of those is divisible by 5. And so if I divide the top by 5, it's a 1. If I divide it by the bottom by 5, it's a 2. With a bunch of zeros. And there it is. Okay? But again, we combine these into single logarithms on each side by using those properties logarithms. We condense things down into one logarithm. And then using that special property to get rid of the logarithms is just a matter of writing each side of the equation as the exponent. We choose the base that's going to cancel the logarithm, and then we solve whatever's left, okay?